Okay, let's look at main concepts of drug interaction with human body. When I'm saying drug, I mean any chemical compound of interest. It can be active pharmaceutical ingredient, it can be poison, it can be just some benign compound. I'll use the word drug for everything. So we'll look at so-called receptor concept, the nature of drug receptors, drug parameters, affinity and efficacy, and at Langmuir isotherm that you may know. When a drug molecule comes to some specific place, some specific molecule in human body, it can interact, bind it to this molecule, reversibly bind, and change action of that very molecule. That's example of action of opioid receptor agonist. So our drug molecule is coming, binds, and makes a complex. This is formula of insulin receptor that is influenced by different compounds. Another example is transmembrane receptor. Protein changes its conformation and changes transmembrane transport. There are thousands and thousands of different known receptors in human body. So, what kind of rules are running this event? First, drug effect is directly proportional to the number of receptors occupied. It doesn't matter how much of your drug compound you have. It's important how many of receptors are interacting with the drug at that given moment. When a drug receptor complex dissociates, drug effect disappears. Next, terms are affinity and efficacy. Affinity, the ability of drug to combine with receptor to create drug receptor complex. Larger is affinity, lower concentration of drug you need. Efficacy is ability of drug receptor complex to initiate the response. You may have drug that binds with drug receptor complex and doesn't give much of effect. You may have drug that binds and gives the necessary effect. Affinity of drug receptor interaction is governed by law of mass action that you know from general chemistry. Now, two new words: agonist, drug with high affinity and high intrinsic activity. Partial agonist, drug with high affinity and low intrinsic activity. Antagonist, drug with high affinity and low intrinsic affinity. The same can be described in terms of kinetics, chemical kinetics. Activation of receptors is directly proportional to total number of encounters of drug with its receptor per second. Pharmacological activity is directly proportional to the rate of dissociation and association. In this case, agonist is drug with fast association and fast dissociation. partial agonist, drug with intermediate dissociation, and antagonist, drug with fast association, slow dissociation. One more theoretical. Here, when drug approaches the receptors alter the conformation of its binding site to produce drug-receptor complex. Again, conformation changes when drug binds to the receptor. So the reason of change of receptor action is change of conformation. This would be dose response curve. So drug interacts with receptor, makes drug receptor complex with equilibrium constant K. Stronger is the complex, lower concentration you need. With concentration is going down, here is, you have a small concentration, large concentration. So this blue drug is more potent than green drug because necessary concentration is smaller to achieve the same effect. Efficacy, on the other hand, gives a measure of action. This is similar to Langmuir as a term that you know from general chemistry. So our action is proportional to some binding constant and to concentration of our drug, and that's a fraction of our receptor occupied. Alternatively, you can use dissociation constant, which is reciprocal to beta, and the expression will be like this. So the curve will go this way, and 50% will give you the value of K. You can look at the same curve in more detail. It's the same, just different coordinates. Or use log scale for x-axis. So you have S-shaped curve. This last is very common in pharmaceutical use. You can use different plots to make it linear. Again, you can look at your biochemistry book if you want. We will not be using them. Similar process in biochemistry we name Michaelis-Menten kinetics. You can see that the equation is practically the same. You have some parameter here, then concentration of substrate, then constant and concentration of substrate. Exactly the same as you had on the slide before. A little surprise, many of drug-related processes are enzyme. So, again, what stands for agonist? Full agonists are able to activate the receptor and result in maximum biological response. Again, response can be very different. It can be poisoning, it can be some additional action, it can be cure, it can be pleasure if you are using, for example, opiate receptor. It can be killing of pain, same story. Partial agonist do not activate receptor completely, causing responses that are partial compared to those of full agonist. Antagonist binds to receptor but do not activate them. So receptor is blocked and agonist cannot work. Inverse agonist reduce activity of receptor. A couple of examples. So heroin is strong agonist of opiate receptor. Narcan is strong antagonist of opiate receptor. It binds to this receptor and prevents heroin or other opiate to bind to it. You can draw such a chart. So functional response will be 0 if you have antagonist. It will be some fraction if you have partial agonist. It will be +1 if you have full agonist. And it can be negative right here. Negative is not much important. Mostly we deal with this area. Competitive antagonism. So we have two drugs, A1 and A2, which compete for one receptor. Only A1 gives an effect. So fraction of active receptor will be beta multiplied by concentration of A1, but it will be divided by expression that has another constant beta 2 and concentration of A2. It's obvious when you have lots of A2, this expression becomes a big one and total fraction goes to 0. It can be more complex picture when you have several sites. So receptor 1 is going to one side and receptor 2 is going to another side. Now you have non-competitive events, so total effect can be coming from this complex or coming from this complex. Two of them can be active. If only A2, nothing happens. These equations are similar to what you have in coordination chemistry, in organic chemistry. So metal ion reacts with ligand 1 and ligand 2. Or in enzyme kinetics, when enzyme reacts with substrate and inhibitor. These equations are exactly identical, but physics can be slightly different. And the last concept, the response curve, we name dose response curve, and usually it's log scale here, and from 0 to 100% response on this axis. 50% response gives you characteristic. For poison, it's LD50, 50% of population dying out. It's very important concept. Old medieval saying, what there is that is not a poison. All things are poison, and nothing without poison. Solely the dose determines that thing is not a poison. Same is true for any other actions. You need appropriate amount of your pharmaceutical active ingredient to have the result. Just any concentration would not help. You need a proper concentration.